Everyone knows binary search, right? Yeah. So here, let's use the divide and conquer approach to understand binary search, especially some details. Yeah. Let's try. Yeah, binary search is a very simple, fast search algorithm, and it is very useful. And many effective, excellent, real-world search algorithms are built based on the binary search. So we need to understand this basic one very well. Yeah. All right, C.1, binary search elimination. So we want to use our elimination method to understand the binary search. Why we can find the element to be searched for so fast. Yeah. So we apply the basic elimination method here. Yeah. All right, so let's look at the question first. Problem number 11, search an ordered array. Yeah. So this time, this condition is very important. Okay? Yeah. Many people make this kind of mistake. Yeah. They forget this ordered condition. Yeah. It's very common. So many people, when they see an array, when they need to search an element in the array, they just apply the binary search anyway. Yeah. But the big problem is if the array is not ordered, so it's very likely you get a wrong result. So first you need to check the condition, ordered or unordered. If it's unordered, you can only use the linear search. Yeah. All right, given an ordered array, yeah, like this, and a search key V, a question, how to find an index I such that V equals A of I. Yeah. All right. Yeah. So here the reference in the textbook. All right. Now let's do the analysis. Let us use the divide and conquer approach of thinking to understand this algorithm. Yeah. Idea. Reduce the problem size by the ordered data property. Here you can see when we solve many computing problems, we apply this basic method, reduce the problem size. Right? In our module 3, recursive algorithms, almost all the questions there, we use this simple method, basic simple method, reduce the problem size. Yeah. So here, divide and conquer. Yeah. So in module 3, we talk about divide and conquer. Yeah. So here we need to learn more about divide and conquer. Yeah. All right, the ordered data property. Yeah. So this property is very important. So we want to use this property to help us reduce the problem size as much as we can. Yeah. When you reduce the problem size, you have many different ways to reduce. Right? Yeah. So if we recall what we did in module 3, we have problem size reduction by 1. Every time we just reduce the problem size by 1. The factorial problem, also the insertion sort, reduce the problem size by 1, right? Yeah, so that's 1. Reduce the problem size by half. Yeah. The binary bit problem. Count binary digits. So the bits, count the bits. So that's to reduce the problem size by half. Another one, variable size reduction. That's the greatest common divisor problem. Yeah. All right, so here, let's see how can we reduce the problem size as much as possible. Elimination method. Yeah. Question, how can we take advantage of the ordered data property? Yeah. Ordered data, this property can help us make good prediction. Good prediction. Yeah. Prediction on what? On the location of the search key. Yeah. The search key somewhere in the given array, we need to have some idea about its location. Yeah. So we want to make that prediction. When we make that prediction, we need to use this ordered data property. Okay, all right. So let's see how to do it. Explore the order property. Here I use a simple diagram to explain the basic idea. Yeah. First, you assume array ordered. Then you want to make prediction. Yeah. But before you make prediction, you can do one comparison. So our basic operation is comparison. So you do first basic operation, one comparison. Yeah. So here I show you the first comparison. If you compare with the last element, that's one option. Then you can choose compare any element in the array, right? Yeah. Here we want to see which one is the best. Which one we can help us eliminate the maximum number of elements. Which one allow us to make a prediction of the search key V in a smallest possible range for its location. Yeah. So when we make a prediction, we predict the location. Location usually we predict in certain range, right? The range, certain range. But the smaller the range, the better, right? Yeah. If the range is too big, then we need to do more work. If we can control our prediction range as small as possible, then we can do less work. Yeah. So that's the thinking here. All right. So let's look at the one special comparison. Compare V with A sub n minus 1. There are two possibilities. Yeah. All right. The best case, if V greater or equal to A sub n minus 1, we treat it as the best case. Yeah, because we know its location immediately, right? Yeah. Greater or equal. If it's equal, we know its location. If V is greater than the last element, we know we cannot find the given key in the array. So then we stop the search. So that's the best case. One comparison, our function returns its result. Yeah. Yeah. All right. But other cases, not that good. Other cases, we need to do more work. So when V is strictly less than A sub n minus 1, we need to do more work. Yeah. Why more work? Because the range is too big, right? The prediction range. Because this time, the range contains all the elements except the last one. Yeah. You can only eliminate the last element from the consideration. So your problem size reduction is very small. Yeah. So we treat it as, so this way, this option is not a good one. Yeah. Yeah. Because the other cases, this part happens most of the time, right? So if we use the probability to look at these cases, the probability should be very high. Yeah. So that means this comparison is a bad one. Yeah. So this one is a bad one. So we want to do better. Yeah. So here, one way to see how to make a good choice, we can connect to the famous Murphy's law here. Yeah. Because here, you can treat as two possibilities. One is the best case, then, non-best case. Yeah, let's call it non-best case. Yeah. But the Murphy's law tells us anything that can go wrong will go wrong. Yeah. So something you try to avoid, but there is some possibility you just hit that bad case. You just hit that bad case. Here, based on the Murphy's law, we don't want to hit this case, right? Yeah, because the prediction range is too big. Yeah. But the Murphy's law tells us we need to seriously consider this non-best case. Yeah. Because there is a good possibility or high possibility it could happen. Yeah. So in order to make this bad one as small as possible. So our goal, make this portion as small as possible. That's the idea. Okay? Yeah. Small as possible, then our prediction range becomes as small as possible. Yeah. Then we will get a better performance. Yeah. So we want to change our comparison strategy. So here, what's our new comparison strategy here? Compare the one right in the middle. The position, you want to choose one right in the middle. Okay? Yeah. So here, what do you mean right in the middle? Yeah. The location in the middle. So we have commonly used the term for it, median. Yeah. So median concept. Yeah. Yeah, because here the array is already ordered. The median location is right in the middle. Yeah. But, so when we talk about the median, what's the definition of the median, right? So here, although we have some basic understanding, but we want a rigorous definition for the median. If there are odd number of elements, if your array has odd number of elements, then it's clear there is only one element in the middle, right? No confusion. So the median is clear, right? So which element is the median? It's clear, no confusion. But the problem is, when you have even number of elements in your array, because in the middle there are two elements in the middle, right? Yeah, because these two elements, they are close to the center equally well. Okay? The center location equally well. Okay? So in this case, we have two medians. One is the left median, another is the right median. Left median, right median. Okay, all right. But we want to make our discussion as simple as possible. Yeah, because usually when we talk about the median, we don't want to specify left median or right median because it's too complicated. Okay? Yeah. So in that situation, we make the left median the default. Left median is the default median. Yeah. So if we do not specify which median, we mean the left median. Okay? Left median is the default median for the even case. Yeah. Then, yeah, because we do not need to, discuss for different cases. We just say compare the given key to the median. Yeah, that's simple. Yeah. All right. So now, here you can see after we change our strategy, comparison strategy, compare the one with the median. Okay. Yeah. The one with the median. Okay. All right. Yeah. So here another way to see this strategy, to understand the strategy. Another way, understand strategy, balancing principle. This is another way to understand. Yeah, here, let me explain a little bit. Yeah. Balancing or balance principle. Yeah. Yeah. So in different context, the balancing principle has different meaning. Yeah. In engineering, there is a balance principle. Engineering regarding the input-output. The input and output, should have the same amount of substance. Yeah. Things like that. So that kind of balance property. Yeah. But here, in our context, yeah, computer science algorithm, in this context, so we have a different balancing principle regarding the data distribution. Yeah, so here, I want to, introduce this basic simple principle regarding the data distribution. All right. Data distribution. What's that? Data distribution. Data. Our given array is the data, right? A given array. And here, when we want to find the appropriate element to compare with the given key V, we split the given array into two subarrays, left subarray and a right subarray. Yeah. So we distribute data into two subarrays, left subarray and a right subarray. Okay? Yeah. There are many ways to distribute the data. Yeah. But here, based on this principle, balancing principle, the best way, so usually we mean the way that would result in the best algorithm, the fastest algorithm. Okay? The way that corresponds to the fastest algorithm usually corresponds to the data you distribute evenly, okay? Evenly in two subarrays. So that's the balancing principle. Yeah. As even as possible. Yeah. You split your data in two subarrays as even as possible. If the data distribution is unbalanced, yeah, one subarray is relatively small, another subarray is much larger, the size difference is very big, that kind of data split usually corresponds to poor performance for your algorithm. Okay? Yeah. So that's the, this balancing principle. Yeah. Yeah. Because here it's a principle. Yeah. Yeah. I explained this principle, the median principle before. Yeah. So that means if you follow this principle, then it's very likely you get the best result. Yeah. But that probability is not 100%. Probably 90-something%, but not 100%. Okay? Because you may have some special cases. Yeah. The probability is small, but that's the special situation you may have. Yeah. But in general, 90% of the chances you would get the best overall performance. Yeah. So here we can also understand comparison with the median element. We can also use this balancing principle to understand it. Okay? Yeah. Because later when we learn the quicksort, we will use this balancing principle another time. Okay? Yeah. And in future, when you do the problem solving on the computing problems, you may need to consider the best case, worst case, many different cases, right? So usually the most balanced way to split your data would result in the best case. The extremely biased distribution of your data would result in the worst case. So we will see that in our quicksort. Yeah, we will have, we will use the quicksort as example to show you this phenomenon. Yeah. All right, so let's move to the next part. Yeah, so here every time you can throw away 1/2 of the elements. Yeah? Because after you compare given key with the median, it could be greater or equal to the median or less than the median. Two cases, right? Yeah. Now you can make your prediction. The given key V must be in one of the two subarrays. If it is in one of the subarrays, left subarray or right subarray, you just throw away the other subarray, right? Because it cannot appear in the other subarray, you can safely throw away approximately 1/2 of the given data. 1/2, approximately 1/2. Yeah, so here, approximately 1/2, half of the data size. Data size is n. So this part, after one comparison, eliminated. Yeah. Eliminated. Okay? Yeah. So that's the, the result of comparison with the median element. Yeah. All right. Next, efficiency analysis. We want to see, to solve the problem, to find the answer, how many comparisons do we need? The best case, the worst case, and the average case. So this C.2, we want to look at that, this efficiency problem. Yeah. All right, the diagram for binary search. Number of comparisons for the worst case. Yeah. The best case, it's easy, right? The best case, when you do the first comparison, you get a hit. Yeah, you hit it. Okay? So the the given key V happens to be the median element. That's the best case, one comparison. Yeah. All right, so now we want to look at the worst case. Yeah. All right, so now we want to do all the possible comparisons. Yeah. So we need to split the given array many times, and we want to see what is the last comparison. Here we need to determine the last comparison. Yeah. So let's do some very accurate estimate. Yeah. We need to estimate, but we want our estimation is very accurate. Yeah. All right. The first comparison, yeah, we can drop 1/2 of the given data. Yeah. So here, which half? It's not important. Left half, right half. We just select one of the two halves. All right. In this diagram. Okay. Then the second comparison, the median of the current subarray. Yeah. So we drop another current half. So this time current half. Okay. So we keep doing this comparison, split, and a drop. Yeah. So we want to see which comparison is the last one. How to represent the last comparison. That's the challenging part. How to precisely estimate the last comparison. All right? Yeah. So let's see. Yeah. Here, let's do a chart here. Yeah. This chart, the top row, the number of comparisons, operations. Yeah. That means comparisons. Okay. The second row, data size. Yeah. After comparison and elimination, what is the data size of the existing subarray? Yeah, subarray. Okay. Yeah. So after one comparison, the data size of the array, subarray that contains the given key is n/2, 1/2. Yeah. So here, don't worry about integer or not. Yeah. Here, some students, you may feel, how about n is an odd integer, right? So n/2 may not be an integer, and later n/4 and n/2 may not be an integer. Yeah, some students, you may worry about that. So here, when we do analysis, we just do estimation. So here we use non-integer, the size for estimate. It's a good first we know it's a very close estimate, right? Yeah. So and it's not necessary exactly the same number. So we just want a very close number expression. Yeah. So don't worry, integer or non-integer. Okay. Yeah. Just half the size. Yeah. All right. Question: at what time should we stop splitting? Because now we want to describe the last comparison. After last comparison, then there is no need to do another comparison. Yep. After the last comparison, our algorithm should terminate. There is no comparison anymore. We want to identify that last one. Or we want to find the mathematical expression for the last comparison. Otherwise, we do not know when our algorithms can terminate. Yeah. So that terminate condition is very important here. Okay, all right. So think about after the last split, if your subarray, yeah, so we use the subarray. So the existing subarray, if it has only one element, this last subarray, if it only has one element, then no further split needed, right? Only one element. You cannot make another split, right? Yeah. So we use this observation to characterize our final split. Yeah. All right. So let's look at the mathematical expression for the final split. All right. After the last comparison, the data size should be less than 1 or should be strictly less than 1. Think about that. Yeah. Why? If it equals 1, think about if the data size, so here the size, if we use line segment to represent the size, okay, line segment, if the difference between these two locations, yeah, two endpoint locations, if the difference is 1, it can cover 2 elements, right? 2 elements. Then 2 elements, you can still make a split, right? Yeah. But think about if the line segment, its length is strictly than 1, then you can only cover 1 element. There is no chance this line segment can cover more than 1 element. Yeah. So that's the reason we say when the data size strictly less than 1, then no further split is needed. So that's the first observation. Okay? Yeah. All right. Then, because the data size, this is the formula expression for the data size, n over 2 to the k. Yeah. That's the current data size. The current data size strictly less than 1, but the data size of after the previous split. Yeah. So this is the data size after the previous split. Yeah. The one here, okay? The previous one. The previous one should be greater or equal to 1. Yeah. So that means you need to do, after you make the previous split, you need one more split. Okay? So here you can see our mathematical description. We should have 2 inequalities. So these 2 inequalities can accurately describe the termination condition, our algorithm termination condition. Okay? Yeah. All right. Then let's just simplify this inequality. After we remove the common denominator, yeah, so we get a integer inequalities. Yeah, integer. I forgot to turn off. Yeah. All right. Yeah. Span. Yeah. Yeah. Anyway. Yeah. All right. I should. Yeah. Should put in airplane mode. Yeah. All right. Yeah. So see. So let's manipulate this inequality. Okay. All right. Yeah. So then we take log base 2. We get this inequality. K minus 1 strictly less than or equal to log base 2 of n and strictly less than k. This inequality. Okay? Yeah. Then, because our goal, we want to estimate the k. K corresponds to the number of comparisons, right? Yeah. The number of comparisons for the worst case. That's the k here. Yeah. All right. So now, we want to represent k in a clear way, yeah, in a convenient way, yeah, here. All right, so let's derive the worst case formula for k, yeah, that k, yeah, k formula, worst case k formula. All right. We start with, yeah, so this is just the inequality, equivalent inequality, yeah, from the previous one, yeah. But this one, you can see one problem here is, we know log base 2 of n may not be an integer, right? Yeah. So log base 2 of n may not be an integer. We cannot assume n is power of 2. You cannot. Yeah. N is a general positive integer. It's not a power of 2. So then, in general, log base 2 of n is a non-integer, positive number. Yeah. Yeah. So here, and we know k is an integer. Yeah. So how can we use an integer expression to represent k? Yeah. So here, this is a non-integer expression. Okay, non-integer expression. But our goal, we want to write an integer expression for k. Yeah. Remember, we did something similar before in our problem counting the binary digits. In that problem, we had a similar situation. Yeah. In that, our old experience, we use floor function, ceiling function, and a floor function to convert non-integer expression to integer expression, right? Yeah. So let's recall in our previous, we use two possible ways to make a non-integer expression to integer expression. One is the floor function, another is the ceiling function. Here, we can use the same way. Yeah. But the hard part is, how do you know which one you use floor function, which one you use ceiling function, right? That's the hard part. Yeah. So here we need to do some more math estimate. Yeah. All right, so let's go back. Yeah. So we have this, previous integer equality we derived from the previous slide. Yeah. So let's go back a little bit. Yeah. So here we want to do slightly better. So let's look at this inequality a little more. We want to tighten this estimate a little bit. Tighten, what do you mean? Tighten. Yeah. Because this inequality can be improved. It has a better estimate form. We can improve it. So it is a little loose. We want to tighten it. So yeah. So what do you mean that? Look at this inequality sign. N is strictly less than 2 to the k. Yeah. So this inequality tells us n is strictly less than 2 to the k. We know they are both integers. N is an integer, 2 to the k is also an integer. There are two integers. But one integer is strictly less than the other integer. So can we improve the inequality slightly? So when I say improvement, can we? Yeah, so here, let's treat this inequality as we find a lower bound power of 2 for n, we find an upper bound, another power of 2 as the upper bound for n, can we make upper bound, lower bound? Can we change upper bound and a lower bound to make the range for n a little smaller? The range a little smaller? We know the smaller the better, right? When we estimate some number, the smaller the better, right? The range, the smaller the range, the better estimate. Okay? Yeah. So here, our goal, we want to make the estimate range a little smaller. Now, the left-hand side, there is an equal sign. Less than or equal. There is an equal sign. That means we cannot increase the lower bound, right? Yeah. Because it has the equal possibility. So we cannot increase the left bound, okay, lower bound. But the upper bound, it's non-equal, right? Yeah. Strictly less than, so we can reduce the upper bound, right? Yeah. Because the upper bound, the current upper bound is strictly greater than n, so we can reduce the upper bound by 1, right? How about that? Reduce the upper bound by 1, okay? All right. Yeah, so here, yeah, another way, reduce the upper bound by 1, so that's n less than equal to 2 to the k minus 1, but this one equivalent to n plus 1 less than or equal to 2 to the k. Okay? 2 to the k. Yeah? So here we reduce the upper bound by 1 integer. Yeah. Because strictly less than, we know at least 1 more. Yeah. 2 to the k is at least 1 more than n. So if we subtract it by 1, then the equal sign could happen. Right? The equal sign could happen. Yeah. So that's the way we lower the upper bound. Yeah. Although only by 1, but slightly better, right? The estimate is slightly better. Yeah. So here we get improvement. Thus n plus 1 less than equal to 2 to the k, that's a better estimate. Better estimate. All right. So with this one, let's take natural, not natural log, log base 2. Yeah. So this log base 2. Yeah. So we have log base 2 of n plus 1 less than equal to k less than equal to 1 plus log base 2 of n. So this inequality, you can see this inequality comparing with that one better. The lower one is better. Better at this lower bound part. Lower bound. Better at this n plus 1, here is n. That's a very small improvement. Very small improvement, but if we want to do accurate estimate, so we take this better version. This is the better version. Okay? All right. Now, from the better version, we can make our final conclusion on the worst case formula for the binary search. Yeah. The final conclusion. So this final conclusion, remember we have upper bound, lower bound, two different sides formula representation. So our final formula, we have 2 versions, one from upper bound, one from lower bound. So the version 1 formula, k sub max, maximum number comparisons, that's the worst case. Okay? Maximum number comparisons for the binary search, we know, corresponds to the worst case. So this one is from the lower bound version. Okay? Yeah. Then formula number 2, this version from the upper bound version. Okay, yeah. And they have different expressions, but they are the same. These two different expressions are exactly the same. And we can prove it using some math tools rigorously. Yeah. Here I skip that. Yeah. Here I skip the proof part. Yeah. And this formula is given in appendix. In appendix, you can find this formula. Yeah. The proof, we need to apply mathematical induction. Yeah. Remember, in the Fibonacci formula, we apply mathematical induction. So here, if you really want to show rigorously, then you can apply mathematical induction to prove it. Okay? So here we skip that, the details of the proof. Yeah. So you can see these two versions both correct. For the binary search, the worst case, they are both correct. Yeah. Yeah. All right. The best case is 1. The worst case is one of the two. Yeah. So you can write either version. Yeah. Either version. Equally well. Equally good. Yeah. All right. Yeah. All right. For the average case, then after we get a best case formula, worst case formula, then the average case formula. So here I want to use this average case to, help you understand how to calculate average case efficiency in the right way. Yeah, in the right way. Yeah, yeah. Because if I do not emphasize this point, yeah, how to calculate average case efficiency, yeah, so many students, so they may use the wrong way to calculate the average case. Okay, yeah. So here, let's see the question: Can you use this simple way to calculate just the best case plus the worst case, then divided by 2 for the average case, for the binary search? Think about this question. Can you use this simple way to do the calculation? Think about it. Yeah. 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 The answer is no. You cannot. You cannot. Okay? Yeah. Yeah. Because here, the best case, remember, the best case occurs only at the root, right? Yeah. Only the median. Only at the median, 1 point. Median. Yeah. So when you have the best case, you compare with the median, you get the best case. Yeah. For the worst case, you have many worst cases, right? Yeah, because you need to, when you reduce, when you do the comparisons all the way down to the bottom level. At the bottom level, there are many cases you can have. So the worst case, you may have many elements. Many elements correspond to the worst case. The best case, only one element corresponds to the best case. Worst case, there are many elements correspond to the worst case. And for the cases in the middle, yeah, not the best, not the worst, other cases, then the number distribution could be different. Okay? So then you cannot assume the average case appears in the midpoint, because this expression corresponds to the midpoint. midpoint of the best case and the worst case. Yeah. But here you can see, actually, for the cases that appear, the best case only one, all right? So the next level, you have a few more, you know. Each level, the number of cases is different. And the worst case at the bottom, you have the largest number of worst cases, okay? So the distribution of different cases, like this triangle shape, it's a binary tree, triangle shape. So the distribution of the data is not evenly. For all the levels, they are not distributed evenly. Only when the data distribution for all the levels are even, then you can use this midpoint formula. If the data distributions for different levels of cases not evenly distributed, you cannot use this midpoint formula. Okay? Yeah. So that's the, you know, one explanation I like to, you know, make you aware of it. Yeah. Let me check the time before the break. Yeah, a few more minutes. All right. Yeah. Yeah. But the next question is how to calculate average case efficiency. Yeah. All right. Yeah. So here, so do not use this formula. All right. Yeah. It's wrong. Yeah. The question, what is the average case efficiency and how to calculate it? Yeah. Yeah. So for the calculation, I like to give you a simple formula to show you how to calculate. What's the right way to calculate it? Okay? Yeah. So that's the, you know, next topic. Next topic, I will use a simple example to show you how to calculate the average case efficiency. Yeah. But before we move that, I want to, you know, give you a little more information about this average case. Yeah. You know, before the break time, so I can talk about, you know, this simple property. Yeah. All right. So let me draw. Let me draw line segment representing best case and the worst case. Best case is a number on the line, so I put it here. This is the best case. Best case, one comparison, right? So the best case. Yeah. Worst case, so this is the worst case. Yeah, because the worst case, we need maximum number of comparisons. Worst case. Okay? All right. So here, you know, here I use this K max number. All right? Yeah. Now, I use this line segment. I want to show you where is the average case location. Yeah. Here we just look at the number. Where is the location? All right? And this is the midpoint. This is the midpoint. Midpoint means 1 plus best case plus the worst case divided by 2, the midpoint. Yeah. All right. Now, here, I want to give you the result. Where is the location of the average case? Location is here, right here. Very close to the worst case. Okay? So that's the average case. Average case is very close to the worst case. Okay? Yeah. How close? So there is a small difference. Between average case and worst case, there is a small difference. Okay? Yeah. Yeah. So what's that difference? What's that difference? All right? Yeah. So here, let me give you the idea about that small difference. How small is that difference? The difference is less than 1. How about that? The difference is less than 1. Okay? The average case, yeah. So here, if I use number of comparison, yeah, I write a simple inequality, okay? Yeah. 0 less than, let me use this, K max, okay? K max is the worst case, minus K AVG, average. The difference is greater than 0, but less than 1. Okay? The difference is less than 1. So you know how close it is. Very close to the worst case. Yeah. Only slightly smaller than the worst case. That property. Yeah. Because the triangle, you can see the triangle, the weight, you know, the big part of the weight toward the worst case part. Yeah. So then, you know, the average is, you know, somewhere here. Okay. Yeah. Just the slightly below, you know, next to the bottom. Yeah. Slightly below that. That's the average location of the average case. Efficiency number. So that property, yeah. This result can be proved, but we need to do a lot of mathematical calculation. Yeah. So here I skip that. Yeah. So you know, it's non-trivial. Yeah. A lot of math work, estimate. Yeah. Here I just give you the result directly. Okay. Yeah. And this result, I may give you some homework questions based on this result. Yeah. So you need to, you know this result. Yeah. But remember, all the content questions for this module 4, we will leave after the midterm. Yeah. So you don't need to worry about these questions in the midterm. But after midterm, I will give you homework assignment number 2 quickly, so these questions will appear in homework assignment question number 2, yeah, after midterm. Okay. Yeah. All right. So now we need to have a break. Yeah. So when you come back at 7, I will show you how to calculate the average case efficiency for the binary search. Yeah. So after that, yeah, because here in the review session today, we only need to explain quiz number 3. I already opened up the answers. I only need to explain 10 questions of quiz 3. Yeah. So our second half, I can complete the remaining part of this topic. Yeah, remaining part. Then we may need 20 to 30 minutes. 20 to 30 minutes we can finish quiz 3 questions. Yeah. All right. Yeah. See you after 7.